morning, afternoon, or evening. How y'all doing today? Welcome back to Morrow's Math Corner. Today, guys, we're going to be learning about radicals. Lesson 2. We're going to wrap up this chapter here today, guys. And that was a wonderful and brilliant welcoming. So everyone out there, that was my class. So my class is here with us live, and we're going to have a great day today. All right, brothers. We're going to learn today how to add, subtract, multiply, divide radicals, solve radical equations. We're going to wrap it all up today. I don't want you to be afraid of this. It's a lot of information. But everything that we use before, I promise, are the building blocks for this. So let's just get right into it. My brothers, last class we learned that if we multiply radicals with the same index, we can go ahead and multiply the insides. So what am I saying by that? If I have the cube root, for example, of 5 times the cube root of 5, of like 15, let's say, since I have the same index, I can multiply them and bam. Okay? We know this already. Today we're going to take it a step further, guys. Today, we're going to add and subtract them. And if you guys remember what we've done before in the past, you can only add like items. All right? It goes back to like chapter 2. Remember when I was like, if you're at the grocery store and your parents say, oh, get me, 2 apples and then 5 pears. You don't have 7 pears. You don't have 7 apples. You got 2 apples and 5 pears. They're not like terms. So in order for them to be like radicals, guys, they have to have the same index and the same radicand. And that's literally it. Once you have like radicals, brothers, now you can start adding or subtracting the coefficients. So look at it like this, y'all. This is 3 square roots of 5x minus 2 square roots of 5x. So I'm going to be left with 1 square root of 5x. And yes, before you ask, of course, the 1 is invisible. But I like to show it to you so you can see there is 1 square root of 5x left over. For letter B, my brothers, can we add these? No, why, my brother? You shook your head, no, why?
An exponent on the x squared.
Okay, that's a great first one. Give me some love. First of all, he realized this is an x squared. This is just an x. Right off the bat, guys, they're not like terms. Why else are they not like terms? Why are they not like radicals?
They have different radicands.
Great vocabulary, bro. This one has a 7, and that's a 5. So you can't do anything. This would literally just stay the same. Very impressed with your vocabulary, brother. Wow, I'm proud of you. How about C, guys? Can we do that one? Don't overthink it. What's the radicand of this guy? No, I'm sorry. That's my bad. What's the index there? What's the index here? 5. That's it. You can't do anything. But Moro, the radicands are the same. Yeah, but for them to be, bless you, for them to be like radicals, they must be the same index and the same radicand. Does that make sense?
Yes, sir.
Promise?
Yes, sir. Yes, sir.
Just for giggles, what if Moro said, let's multiply these? Is that possible? What did I say has to be the same when you say it loud and proud, brother? The index. Okay. Are the indexes here the same?
No, sir.
Okay. But the radicands are, right?
Yes, sir.
Let me give you a little hint. What can I convert these to so that they have the same base? Exponential form. Oh my God. Give me another one. Let's go. That is perfect. So guys, we have 12 times 7x to the 1/3 times 8 times 7xy to the 1/5. Brothers, this is magic what just happened there. I'm so proud of you. Yeah, you cannot multiply those radicals, but you sure as heck can multiply now the same base. What do you do when you multiply the same base, guys? Add the exponents. There you go. Good. Don't be afraid. Good job. So, guys, 8 times 12 is 96. And 7xy to the 1/3 times 7xy to the 1/5. Keep the same base. Add the exponents. That goes to 15. That goes to 5. That goes to 15. That goes to 3. So this is 7xy to the 8/15. I know that this is not what we're doing today, but I wanted to just go back in time to show you this little nuance. But now, back to adding. For letter D, guys, I got 17 fifth roots of 3x squared minus 15 fifth roots of 3x squared. I got a thumbs up here. What do you think, yes? Yeah, they're like radicands. So what do we got left over, guys? 2 fifth roots of 3x squared. Woohoo! Guys, some of my students made this a 9x squared. Guys, is this power of 2 affecting the 3? No, it's not. It's just affecting the x. If it was in parentheses, then it would be affecting the 3x, okay? How about for E, guys? Are these like radicals? Absolutely. So 5 cube roots of x plus 3 plus 15 cube roots of x plus 3 equals 20 cube roots of x plus 3. Let's go. Questions, comments, concerns, problems, issues, dilemmas. So guys, what has to be the same in order to add or subtract radicals? The index and the radicand. Good job. Make sense?
Yes, sir.
May I continue?
Yes, sir.
One of my students said, Moro, these are super awesome. You can't do any of these. Thank you, sir. And I laughed because I was like, yeah, you got to first do what do you think, guys, before we can determine if they're like radicals or not. Yes, sir, my brother.
Well, first they all have the same index, right?
Well, they do have the same index.
But you have to make them have the same base.
There we go. We want to see, they have the same index, but do they have the same radicand at this point right now? No. But can't I break this guy down into, let's say, 3 times 4? Guys, what's this square root of 4? 2. So this is 2 square root of 3. Plus 75. Me personally, I'm going to think perfect squares. 3 times 25. What's the square root of 25? 5. So this is 5 square roots of 3. And then here I have a square root of 3, which is a minus 1 square root of 3. Why did you put the 1, Moro? Because I'm a human being. And I like to show myself that it's a negative 1. That way I personally think it helps me out. So what's 5 cube roots of 3? Sorry. What's 5 square roots of 3 plus 2 square roots of 3 minus 1 square root of 3? Say it. 6 square roots of 3. Good job, bro. Woohoo! Okay, guys. Remember that whenever you start with an even number, what's the one division I suggest strongly to start with? 2. So guys, what's 2 times... 2 goes into 250 how many times? That's right. Okay. Now, does 5 go into 125? 5 times 25. Boom! 25 is a perfect square. So this is 5 square root of 10. Cube root of 10. Come on, Moto. Yes, sir.
Wouldn't the 25 be considered?
Actually, wait a second. Moto just made a very bad mistake. And thank you, Gabriel. Oh, my boy. Sorry. Guys, I'm looking for cubes, just like my boy said. And I was not paying attention. And I apologize. I got to practice what I preach. Thank you, my brother. You're my mom. You're my boy. We're looking for cubes, Moto. Cubes. So yeah, bro. 125 is a perfect cube. A 5, and a 5 comes out as a 5 with a cube root of 2 left over. If I divide 54 by 2, I get 2 and 27. What's the cube root of 27? So this is plus 3 with a cube root of 2 left over. And then 16 is 2 and 8. What's the cube root of 8? 2 with a cube root of 2 left over.
Wouldn't it be minus 2?
And yeah, that's a minus. Yep. Thank you, son. So what do we get here, guys? What's 5 cube roots of 2 plus 3 cube roots of 2 minus 2 cube roots of 2? 6 cube roots of 2. That's it. Is that making sense, guys?
Yes, sir.
All right. C. How can I break down square root of 20? Or I would have thought of 5 and 4 for a perfect square. What's square root of 4? So 2 times 14? 28, square root of 5. This is 5 and 25. What's the square root of 25? So that's 5, square root of 5. What's 28 square roots of 5 minus 5 square roots of 5? Woohoo! Let's go. Let's go. And now for a fourth root, how many of one value do I need to pull it out? 4. So let's think about that. This is 2 and 16. Does anyone know the fourth root of 16 by chance? Okay, it's 2. But to be fair, if you don't know it, guys, break it down. Keep going all the way to your prime factors, brothers. And then remember, we're looking for sets of 4. So a 2, a 2, a 2, a 2 comes out as 1, 2 with a fourth root of 2 left over. Excellent, sir. Same thing with 48, my brothers. This is 2 and 24. If you need to break this down, 2 and 12. There's no shame in this. 2 and 6, 2 and 3. And then once again, a 2, a 2, a 2, a 2 comes out as 1, 2. But I have a fourth root of 3 left over. Uh-oh. Can I add these together?
No, sir.
No, so we're done right here. This is fully simplified, but you can't add them because they don't have the same radicand in this case. Does that make sense, guys?
Yes, sir.
Questions, comments, problems, issues, situations, dilemmas?
No, sir.
May I continue? All right. All right, brothers. What happens when you're multiplying radicals? We already know this. We know how to distribute. We know that we can multiply radicals if they have the same index. But there's a phenomenon that we're going to see here that we mentioned before, but now we're going to see it live. Check it out, guys. The square root of x times the square root of x will always equal x. Why? Well, square root of x times the square root of x equals the square root of x squared. Guys, don't the radical and the power of 2 cancel? So I'm left with x. So what is this theory telling us? The square root of a number times its exact image will always equal just simply the radicand. So the square root of 19 times the square root of 19 is 19. Square root of 5x times the square root of 5x is 5x. So when we're multiplying, a square root of 6 and we're distributing, remember there's a coefficient here, so 3 times 1, that's 3 square roots of 6. But this is 5 times 6. Why? Guys, what's square root of 6 times square root of 6? There it is. So this is going to be 3 square roots of 6 minus 30. Do you see that, y'all?
Yes, sir.
Take your time. Think about it. Process it. Write the rule up there at the top. Write the y in green to show yourself why it equals x. And now we just FOIL like normal. 3 times 5? 15. 3 times square root of 7? 3 square roots of 7. Negative square root of 7 times 5? Guys, 5 times negative 1, dude. Negative 5 square root of 7. Negative square root of 7 times square root of 7? Negative square root of 7 times square root of 7? Negative 7. Let's go. Excellent. Now add like terms, guys. What's 15 minus 7? 8. 3 square roots of 7 minus 5 square roots of 7. Woohoo! Excellent, gentlemen. Excellent. Excellent. Proud of you, bro. Oh, I see people already working on C. I love it. So 3 times 2 is? 3 times 4 square root of 5? Yes. 2 square root of 5 times 2? Let's go. Now this one's a good one. 2 square root of 5 times 4 square root of 5. Yes, you can. They have the same index. You can totally multiply them. What's 2 times 4, guys? And then what's square root of 5 times square root of 5? Let's go. So it's going to be 46 plus 16 square roots of 5. Does that make sense?
Yes, sir.
Promise?
Yes, sir.
Okay. Guys, what does this exponent mean when we're dealing with a polynomial? No.
It's 2 of them.
Thank you. Yes. Let me show you the pitfall, guys. If it was just a monomial squared, yeah, that goes to this and to this, so that'd be 4 times 5, and that would equal 20. But I have a binomial. So when you're squaring a binomial or a polynomial, you're repeating the multiplication that many times. So this is really, like my boy said, who's on fire today, it's repeated multiplication. So please do not square this and square that. No. No. That's a big fat no, my brothers. This power of 2 means it's double multiplication. You're multiplying it times itself twice. And now let's FOIL. So 2 square root of 5 times 2 square root of 5. No. 2 times 2 is 4. What's square root of 5 times square root of 5? 5. 2 square root of 5 times 3 square root of 2. 2 times 3 is? And then square root of 5 times square root of 2 is? Guys, can you multiply the insides when they have the same index? Yes.
Oh, yeah.
Come on, guys. We got to know these things. Now, 3 square root of 2 times 2 square root of 5. Come on your own. Guys, what's 3 times 2? 6. Square root of 2 times square root of 5. 10. There it is. Square root of 10. And then 3 square root of 2 times 3 square root of 2. 9. There it is. 9 times 2. Woohoo! So that's going to be 38 plus 12 square roots of 10. Very proud of you. Talk to me. We're doing great, guys, by the way. We're doing great. We're right on target. Questions?
No, sir.
Are you sure, brothers? Continue? Let's go. Okay, guys. We're like almost halfway there, okay? We're almost there. We're doing great. I'm so proud of you. Let's go. Guys, we're going to have situations sometimes where you have a radical in the denominator. That's unfortunately an illegal situation. You're not allowed to have radicals in the denominator. It just will not happen. You have to get rid of them. You have to convert them. This process is called rationalizing the denominator. I'm going to go ahead and read the technical stuff, and then I'm going to tell you in Moto's words what that means. Guys, in order to rationalize the denominator containing a single square root, simply multiply both the numerator and the denominator by the square given in that denominator. I'm going to explain what that means. Before we do that, let's have a little reminder. Square root of a times the exact square root of itself will always equal the radicand. When you multiply any radical times any square root times itself, it will result in the original radicand without the square root. Okay, so you ready?
Yes, sir.
What the heck does this mean in English, Moro? Guys, we're going to be given a radical in the denominator. And you're basically going to multiply to both the numerator and the denominator a value that creates a perfect radical. In this case, it'd be a perfect square. Guys, in a square root, which is here, how many of the same value do I need to pull one value out? Two. How many 5s was I currently given?
1.
How many more would I need to get 2?
1.
Thank you, guys. So, guys, that's why you're multiplying by the square root of 5. Now you're going to have 2 square root of 5, and now we can use our knowledge. What's the square root of 5 times the square root of 5? 5. Bye-bye, Lola. You're done. You have rationalized the denominator. You have rationalized the denominator. Rationalizing simply means multiplying what's missing to create a perfect square or a perfect cube or a perfect fourth, depending on the index. Does that make sense?
Yes, sir.
For real? Okay. Let me show you what most people are going to do on B, and then let me show you what I would do on B, and let me reiterate that there's no shame in either way. Most people, they're in a hurry and stuff. You're just going to go ahead and multiply to create the perfect square. Guys, how many 12s was I given here?
1.
How many more do I need for a perfect square?
1.
One more. So this is going to be the square root of 84 over 12, which is fine. However, we always have to try to see if we can simplify. So this is 2 and 42. This is 2 and 21. This is 3 and 7. In square roots, I'm looking for sets of 2, right? So a 2 and a 2 comes out as a 2, with a square root of 21 left over 12, and then I can reduce square root of 21 over 6. There's nothing wrong with this. There's nothing wrong with this. I promise you. However, there is a more efficient way. Let me know when you're ready for me to teach that to you guys. And thank you for your honesty. All right, guys, you ready?
Yes,
All right, brothers. What I would do, and again, guys, I get it. I've been doing this a long time. But I've been harping over and over, probably like you're sick of me saying this. Know your perfect squares, know your perfect cubes. Know your perfect squares, know your perfect cubes. This is why it's important to know that. Me personally, I saw this and I went, oh, this is 3 times 4. So I rewrote it, me personally, as 2 square root of 3. And now what this does, my brothers, is now I don't have to simplify later. How many 3s do I have down here in the denominator? How many more do I need to get a perfect square? So I do this, and guess what? In one fell swoop, 2 times 3 is 6, and I get to where I need it to be. There's nothing wrong with multiplying by square root of 12. Nothing wrong. However, if you can see it, if you can simplify it, if you do that, it's going to save you time in the long run. Does that make sense, guys? Okay. Brothers, a lot of my students get confused here when they see that x is greater than 0. Let's just go back in time real quick to chapter 8. Remember that there's 3 restrictions for domain. Domain can be all real numbers except restriction 1. If x is in the denominator, remember you had to set the denominator not equal to 0. Restriction 2. If x was in a square root, you had to set x to greater than or equal to 0, because you cannot have negatives inside of a square root. They are imaginary numbers. And then possibility 3 is if you have a x in a denominator and in a square root, then x has to be set to just greater than 0. This is how you find domain. And in this particular case, guys, you're going to see this in higher level math. They're going to give you the domain here. You could have found it yourself, but here, they gave it to you. X has to be greater than 0. Because if you have a negative here, guys, you're going to have the square root of -2, and that is an imaginary number. Get rid of that. Thank you, my brother. Okay? Does that make sense? So, guys, how many 2x's do I have down here in the denominator, in this denominator here? How many do I need to get a perfect square?
2.
So I need 1 more. So, brothers, don't overthink this. This is 4 square root of 2x over 10x. And then I reduce. For those of you that are saying, how did this man get 10? Guys, you have 5 times 1, which is 5. And what's square root of 2x times square root of 2x? 2x times 5 is 10x. And then I reduced by dividing 2 to both top and bottom, to the numerator and denominator. Does that make sense? All right, let's do this. Now, sometimes you're going to have to rationalize, and it's not a square root. Sometimes it's an nth root. Cube root, 4th root, 5th root. Same procedure. You ask yourself, how many do I need to pull 1 out? How many was I given? How many more do I need? For example, guys, in a cube root, how many of one value do I need to pull one of those values out? How many 6's do I currently have?
1.
How many more do I need?
2.
So, guys, I use exponents. And I'm going to show you why I use exponents now. When you multiply this, this is going to be, the cube root of 36 over 6. Now, let me show you why and how that worked out and why it's so beautiful. Remember that I kept saying, guys, the goal is to make a perfect radical. Guys, what do you do to the exponents when you multiply the same base? Add them. So isn't the cube root of 6 times the cube root of 6 squared, isn't that really the cube root of 6 to the 3rd? Guys, that creates the perfect radical. I heard a "oh" out there. Yes, that's what I want. If you don't see it, if you did not get that "oh" moment, that aha moment, please raise your hand so I can do it again, because I need it. Yes. Okay. Thank you. How many 6's do I need in total here to pull 1 out?
3.
How many have I been given?
1.
How many more do I need?
2.
I'll multiply here. So this is the cube root of 36. Now, here. This is the cube root of what's 6 times 6 squared, bro?
36 times
No, you're not listening to me. 6 to the first power times 6 squared. What do you do when you multiply the same base?
6, 3.
6 to the third power. Isn't the cube root and the third power, don't they cancel? That's why I complete this perfect square, guys. This perfect radical, rather. The cube root of 6 cubed is 6. I'm done. Why? Because I created this perfect radical. When I multiplied what was missing, I'm creating that perfect radical. Thank you. Yes, no, maybe kind of sort of, guys.
Yes, sir.
Promise?
Yep.
All right. When we get to larger radicals, larger indexes, I strongly suggest breaking numbers down. For example, this is the cube root of 5 over, brothers, can't I break down 18 into 2 times 9 and 3 times 3? So if I broke this down, wouldn't this be 3 squared times 2? Hold on, I heard a lot of silence here. Guys, doesn't 18 break up into 2 times 9?
Yes, sir.
Doesn't 9 break up into 3 times 3? So can't I represent 18 as 3 squared times 2?
Yes, sir.
Yes or no?
Yes, sir.
Okay. How many of one value do I need in a cube root to pull it out?
3.
How many 3s was I given?
2.
How many more do I need?
1.
How many 2s was I given?
1.
How many more do I need?
2.
Do you see the magic here?
Yes, sir.
Now the cube root of 5 times the cube root of 3 times 2 squared, that's going to be the cube root of 60. And now, check it out, guys. Isn't 3 squared times 3 3 cubed? Guys?
Yes, sir.
Isn't there an invisible 1 here, right? So isn't 3 squared times 3 3 cubed? What's the cube root of 3 cubed? Guys, don't you pull it out? Don't you have 3 3s?
Yes.
So what's the cube root of 3 3s?
3.
Are you not seeing this?
Yes, sir.
Talk to me if you don't see it, please. It's my job. Guys, what's 2 to the first power times 2 squared? What's the cube root of 2 to the third?
2.
Done. So I have the cube root of 60 over 6. Are you picking up what I'm putting down?
Yes, sir.
Okay. This is 4th root of 2 squared x cubed. Guys, how many 2s was I given?
2.
How many more do I need to create a perfect 4th root?
2.
Yes. How many x's was I given?
3.
How many more do I need for a perfect 4th root?
1.
Let's go. So this is 6 times the 4th root of 4x over, what's 2 squared times 2 squared, guys? 2 to the, what's the 4th root of 2 to the 4th?
2.
What's x cubed times x? X to the 4th. What's the 4th root of x to the 4th? Simplify. Are you with me here, guys?
Yes, sir.
Promise?
Yes, sir.
If you have a question on any of these, please ask. How are we doing?
Good.
We're almost done. You guys have been amazing. Very proud of you. Continue?
Yes, sir.
Hold on, brother. Talk to me. No, I see you analyzing. I'm proud of you.
No, I just, because it's 2, 2, so you need 2 more.
Correct, sir. Great job, kid. Proud of you. Thank you for analyzing. Forward, guys.
Yes, sir.
I don't want to leave you behind. You sure?
Yes, sir.
Okay. Almost done. Almost done. We got conjugates. Guys, we've dealt with right now radicals just being singular in the denominator. Sometimes you have a sum of a number and a radical, or two radicals. And when that occurs, you also got to get rid of that in the denominator. And the way you get rid of any sum or difference of radicals is by multiplying by what's called the conjugates. Conjugate's very easy to find. 1 minus square root of 5, the conjugate would be 1 plus square root of 5. You literally change the middle sign. Square root of 3 plus square root of 2 literally would become square root of 3 minus square root of 2. You just change the sign. Why does this help, Moto? Well, if we go back in time to chapter 6, we learned that when you multiply an A plus a B times that same exact A minus B, it's a difference of squares, you get the first term squared minus the second term squared. So this would be A squared minus B squared. You apply this anytime you have an exact A plus an exact B being multiplied to that same exact A minus that same exact B. If you want to go the long way, this is how you would go the long way. I'm going to do this once for you, but after that, we're going to do it the correct way, the most efficient way. But you stress out, you forget. 5 times 5 is 25. 5 square root of 7. Negative 5 square root of 7. And negative square root of 7 times square root of 7 is negative 7. 25 minus 7 is 18. And we're good. We're golden. There's not a darn thing wrong with that. However, it's time consuming. It's more steps. And we're all human beings. With more steps, the more chance of making a mistake. So, Moto, what are you proposing? I'm proposing you learn finally difference of squares. My brothers, the 5 is my A term. That's my first term. The square root of 7 is my second term. That's my B term. The minus is just separating them. So use the difference of squares. I got 5 minus square root of 7 times 5 plus square root of 7. Hey, difference of squares. So I'm going to go 5 squared minus square root of 7 squared. And that equals 25 minus 7. That was me. I should have silenced it. But thank you, bro. And that's 18. That's a lot quicker, no?
Yes, sir.
It's a lot more efficient. But can you do it the long way if you forget, you're stressed, you have a bad day?
Yes.
Yeah, absolutely. It's going to take a lot longer. Let's look at B. If you need to do it the long way, that's fine. But it's the first term squared minus second term squared, which is going to be 36 minus 12, which equals 24. Does that make sense, brothers?
Yes, sir.
100%? Okay. Sometimes, guys, we're going to have a denominator with two radicals or a sum of radicals and numbers. Don't be afraid. Rationalize by simply multiplying by the conjugate. So, for example, how do we rationalize this bad boy? We're going to multiply literally by the square root of 5 plus the square root of 2. The conjugate. Square root of 5 plus square root of 2. Now we're going to FOIL. 3 square root of 2 times square root of 5 is 3 square roots of 10. And then 3 square root of 2 times square root of 2. Take your time with this. There's an invisible 1 in front of the square root of 2. So 3 times 1 is 3. Square root of 2 times square root of 2 is 2. Great job, guys. Over. Take your time with this. First term, which is square root of 5, squared. Minus second term, square root of 2, squared. So this is 3 square roots of 10 plus 6 over 5 minus 2. Beautiful. That's 3 square roots of 10 plus 6. I heard somebody say it. Great job. Over 3. And the last step, remember you're dividing this denominator to that coefficient and that one, my brothers, giving me square root of 10 plus 2. Digest that. Check it out. It's not that bad, is it?
Nope. No, sir.
It's not that bad. If I want to rationalize b, I literally rationalize it by multiplying by the conjugate, which I literally just changed the sign. And now I'm going to distribute. So what's 2 square root of 7 times square root of 3?
2 square root of 21.
Boss. 2 square root of 7 times square root of 5.
2 square roots of 35.
Woohoo! Square root of 3 squared minus square root of 5 squared. For those of you who may be like, whoa, why did he do that? Because of difference of squares. No sarcasm, guys. That's why I multiplied by the conjugate. You're already immediately guaranteed creating a difference of squares. Guaranteed immediately. So that's why I'm taking the first term, square root of 3, squaring it. Minus second term, square root of 5, squaring it. This make sense, guys? So this is going to be 2 square root of 21 plus 2 square root of 35 over 9 minus 5, which is 2 square root of 21 plus 2 square root of 35 over 4, which would be square root of 21 plus square root of 35, both of them over 2. How are we vibing with this, guys? Why don't you guys try to do C? Do your best not to look up. I'm going to do it silently. Let's see if we both come up with the same answer, okay? Please do your best not to look up. Once you're done, brothers, look up. Did you get what I got? If not, please let me know. We're doing great with time.
Let's go.
You got it?
Yeah.
Let's go. Let's go.
Not bad.
Talk to me, my brothers. Let's go. Give it up, bro. My brother. Let's go. We Gucci here, guys?
Sure.
We're Gucci. Let's do it.
Oh,
So, talk to me.
no, I just realized that the square and they cancel out. They just cancel out.
Yeah, so square root of 6 cancels out with its power of 2. Thank you, Papa.
Yes, sir.
Yes, sir. Let's go. All right, guys. Believe it or not, now we're getting to the easier parts. Yeah, promise. Yeah, it's easier. Guys, a radical equation is an equation when you have a radical. Not rocket science. Just like an absolute value equation was one with an absolute value. Well, now this one has a radical. The easy thing here, guys, is to simply, number one, isolate the radical. Get rid of anything that's being multiplied to it, added to it, divided to it, subtracted from it. Get it alone. Then, cancel out or eliminate the radical by raising both sides of the equation to the power of the index. Guys, what happens when you square a square root? It cancels. How do you think you cancel a cube root? By raising it to the third power. Fourth root, raising it to the fourth power. Exactly. So if you want to get rid of a radical equation, you literally raise it to the power of the index. And then you check your answers, of course, to see if you have any extraneous solutions. So guys, is the radical by itself here? What do I do? How do I get rid of that square root? By raising it to the second power. What happens to the square root when I raise it to the second power? They cancel, my brother. 5 squared is 25. And now we solve like the bosses that we are. And x will equal, woohoo! It's not bad at all, is it? Let's look at B. Subtract 3 to both sides. Now I got my radical alone. We'll square it. The square root and the power of 2 cancel. Going to add 3 to both sides. 2x equals 28. And x equals 14. Let's go. Man, let's go. C is the same thing, guys. I don't want to bore you. Let's just move on to D, though. I definitely want D. Okay. And D is a great example because something very particular is going to happen here. And I wanted to show you this now, guys, instead of you doing it at home for homework. Does anyone notice that when you subtract 7 to both sides, you have the square root of 5x minus 1 equals a negative 2? Stop, because that's no solution. Ooh. You may say, why, Moto? Guys, think about this. What perfect square comes out as a negative? Nothing. Nothing. But sir, negative 4 times negative 4 is 16. Yeah, but the square root of 16 is 4. So you may want to write down the following. Similar to the absolute value, almost identical. But, you may have forgotten it. Guys, if you have a square root of x that's less than 0, all of these, by the way, are, let me label this properly. These are no solutions. Okay? So, sorry. If x is less than 0, guys, no solution. If it's less than or equal to 0, it's still no solution. It can equal 0, but it cannot be less than 0. So that doesn't work either. Now, if I have the square root of x is less than any negative number, that's a no-go. And if it's less than or equal to any negative number, that's a no-go, guys. So if you ever have a square root that's going to be equal to or less than a negative, stop, I promise you. It's no solution. Now, if you look at e, though, I did this on purpose, you're going to have a negative once again. But you're going to have an odd index. Are we allowed to have negatives in odd indexes? Yes. Yes, because think about it. -1 times -1 times -1 is -1. -2 times -2 times -2 is -8. So you can have negatives inside of the radicand for odd indexes. So now, how do I get rid of a cube root? Thank you, brothers. Woohoo! Those bad boys cancel. And I got me here. Let's go. Now we're just going to solve like the bosses that we are. And for any ladies out there listening to these videos, you are bosses as well. I just teach an all-boys school, so don't think that I'm not thinking about you ladies out there watching. It's true, it's true. Okay. Does that make sense? Sure. And then last but not least, guys, I just want you to set this up. What do you think I would do with this 1/2?
You multiply it to the other side.
No. What is that half? How do I put it in radical form? Let's go. So wouldn't that just be 5x, guys, minus 1? Now start the process, right? Now I'm already doing it, so let's just do it. That's right, brother. And then you add that 1, dog. And you got 5x equals 50. And bada bing, bada boom. Woohoo! Does that make sense, guys? Guys, I'm very happy to announce that we have one lesson left.
Let's go.
And you have done amazing. Now, I know that I've thrown a lot at you, but be fair. Isn't it all kind of just build on itself, right? I'm very proud of you, my friends. Very proud of you. May I continue?
Yes, sir.
Okay. Last but not least. My brothers, in the beginning of the year, we talked about real numbers and imaginary numbers. I told you, I promised you, we'll learn about them later. Later has arrived, has become a reality. Guys, whenever you have a negative inside of a square root, it is a value. It's not a real value, so that's why it would be no real number, but it is called an imaginary number. An imaginary number or an imaginary unit is represented literally by this letter I. So if you ever see an I, what that really means is a square root of -1. Or if you ever have a square root of a negative, you pull that negative out by taking an I out. When you multiply I times I, guys, you keep the base and you add the exponents, you get I squared. I squared equals -1. I times I times I is I cubed, which equals -I. And I times I times I times I is I squared times I squared, which is -1 times -1, which is +1. Every 4 i's can come out as a value of 1. Every 4 i's equals a value of 1. A complex number, guys, is a number that has a real part, which is the A, and an imaginary part, which is the BI. That's called a complex number. Simplifying imaginary units is easy peasy. What I strongly suggest is take out the negative immediately and then try to simplify the radical. For example, here, I'm going to take out that negative as an I. Square root of 6 is 2 times 3. I don't have any pairs, so this is simply I times the square root of 6. Square root of negative 27, me personally, I'm going to make this an I immediately. And now I'm going to simplify. It's 3 times 9. Square root of 9 is 3. This is 3i with a square root of 3. Negative square root of 64, that's just 8i. How'd you do that so fast? Well, the negative square root of 1 is an I. Come on, Moto. And the square root of 64 is 8, so 8i. Square root of negative 18, take out that negative as an I. 18 is 2 and 9. Square root of 9 is 3. So this is 3i with a square root of 2. Simplifying radicals with I, with a negative, is simple. No longer will you put not a real number. Nope. Now you know how to work with that negative. It's an I. Bless you. Make sense? Yes, sir. Talk to me.
He's on C.
On C, yeah. What's the square root of 64? It's a perfect square.
Oh, yeah.
It's 8. But let's answer the real question you had. My brother just had a moment, and he didn't know what to do. He forgot just for a second. We are all human. Break it down. I definitely do not suggest this, but in a pinch, you get nervous, you get scared, you forget, do it. And then just remember, my brother, square roots, we're looking for pairs of 2, sets of 2. So a 2 and a 2 comes out as a 2. A 2 and a 2 comes out as a 2. A 2 and a 2 comes out as a 2 times that I, which is 8i. Thank you, man. All right. Let's simplify each of these. You should see this as 4 minus 6i. You're done. Moro, don't you multiply the negative times the negative? No. Order of operations. Parentheses first, and radicals are considered parentheses. This is 8 plus, this is 2 times 16. Square root of 16 is 4. So this is 4i square root of 2. And then I did this on purpose. There is no negative inside the radical. So you don't put an I just because there's a negative outside of it. This is 5 times 4. Square root of 4 is 2. So this is 4 minus 2 square root of 5 over 2. This denominator gets divided to both of these coefficients, which is 2 minus square root of 5. Adding and subtracting i's is just like adding like terms, guys. If they're i's, they can add together. If they're not like terms. So if I have negative 3 plus 8i minus parentheses 7i, 7 minus 3i, I'm going to distribute that negative. Give me negative 3 plus 8i minus 7 plus 3i. Now I combine like terms. So that's going to be negative 10 plus 11i. And that is the form of a complex number. You got to put the real part first and then the imaginary part. For B, this is 6 plus 7i plus a negative, minus 4i, minus 4 plus 3i. Add like terms here. That's right, say it. 2 plus 10i. No shame in that. Perfect. And then last but not least, distribute that negative, making that a positive 7 plus 6i. So what will we get here? Let's go. 12 minus 4i. Woohoo! When you're multiplying, guys, you multiply like a normal variable. Remember that I has an invisible exponent of 1 as well. So when you multiply an I times an I, it's I squared. And I squared equals negative 1. Why is this useful, Moto? Check it out. 5i times 4 is 20i. But 5i times 2i, check this out, guys. This is negative 10i squared. Beautiful. What is the value of I squared? What's a negative 1 times that negative 10? So this is going to equal 10 plus 20i. Did you see that, brothers?
Yes, sir.
Don't be afraid to foil. Negative 6 plus 2i plus 18i minus 6i squared. What does that become?
6i squared.
No, what's I squared?
Negative 1.
Negative 1 times negative 6? 6. So this is negative 6 plus 20i minus plus 6, which equals simply 20i. Okay, look, what's negative 6 plus 6, Papa?
Oh, no.
They can't, right? Does that make sense?
Yes, sir.
Ooh, what is negative square root of negative 36?
6i.
Bam. Times square root of negative 9?
3i.
Let's go. What's 6 times 3?
18.
I times I.
I squared.
What is I squared? Let's go. Woo! This should be now, this is 5i times 2 minus I square root of 5. Big difference. FOIL, 6 minus 3i square root of 5 plus 10i minus 5i squared square root of 5. What is I squared? So this becomes 6 minus 3i square root of 5 plus 10i, perfect, son, plus 5 square roots of 5. And I don't have like terms. Now you may say, Moto, the square root of 5 and the square root of 5. Yes, but are 3i and 5 like terms?
No.
So we can't add those. That makes sense?
Yes, sir.
Not that bad, right? A lot. Yes, a lot. But not that bad, right? I promise we're almost done. 2 more things. Guys, good news. We already did this. A conjugate is a conjugate is a conjugate is a conjugate. Whether it's just radicals or i's. To find the conjugate, you change the middle sign. Remember also, the difference of squares works for I as well. Let me show you how. If I multiply 8 minus 5i times 8 plus 5i, I can go ahead and do the long route, which would be 8 times 8, which is 64, plus 40i minus 40i minus 25i squared. This is the long way. I'm not going to do this, but if you need to. Guys, what does negative 25i squared become? Positive 25. So this would be now 89, period. Moro, how would you do that using your little difference of squares formula? Very easy. Check it out. You would go first term squared minus second term squared. That's 64 minus 25i squared, which becomes positive 25, which then goes to 89.
Pretty simple.
Not bad, right? 2 minus 4i times 2 plus 4i. Well, I'm going to, me personally, take first term squared minus second term squared. Four minus 16i squared. Perfect. And what does that become, Papa?
4 plus 16.
Woohoo! Let's go. Let's go. Yes. All right, guys. I promise we're right there. Now, how do we use this skill? We rationalize denominators with i's this way. Why do I got to get rid of an I? Because an I is a radical. You're not allowed to have radicals in the denominator. So, Moro, how do I get rid of this? Multiply by the conjugate. Negative 4 times 2 is negative 8. Negative 4 times negative 3 is 12i. I times 2 is 2i. I times negative 3i is negative 3i squared, which becomes positive 3, just positive 3, which then equals negative 5 plus 14i. I know I went extremely fast. I'm going to chill for a second. Oh, but I see a lot of ballers that are right with me, and they're already on B. So I'm going to have to keep up with the ballers. I'm going to multiply by the conjugate. Distribute. I'm not talking because I think you guys know what's going on here. Remember that 9i squared becomes a negative 9. So that gives me negative 5 plus 15i over first term squared minus second term squared. That's going to be negative 5 plus 15i over 1 minus 9i squared. That becomes positive 9. So that becomes negative 5 plus 15i over 10. And can I simplify that further? What can I take out? A 5. So I have a negative 1 plus 3i over 2. Again, I know I'm going very fast. Last but not least, we don't need a conjugate for this one. We just need to get rid of the radical. So how do you think I can get rid of an I? How many other i's do I need to get?
One more.
One more, very good. So I'm literally going to multiply by an I. Do I need to multiply by the 2? No. 5i. Can I multiply by the 2? Yes, but it would be inefficient. So this is going to become, remember, 6i squared becomes negative 6 plus 5i, and 2i squared becomes negative 2. Divide it to both. This will be 3 minus 5i over 2. And then I promise you guys, I have one thing left, and it's super simple.
Mr. Moore,
Brother,
on the
please.
like on a test, would you
Yeah.
grade it if it's the wrong way?
The question was, oh, no, I'm not gonna, no. The question was, Moto, if I have this, but on the test, I write it like this, 5i minus 6 over the negative 2. Am I gonna mark that wrong? No, bro. But, just to be fair, this will not be the form on the SAT. It'll be this form here. But no, I'm not going to mark it wrong because your math is correct. Thank you, brother. You ready for the last thing? Okay, guys. Promise, this is it. These 4 examples, I promise. You guys have been amazing. Guys, we're going to learn how to simplify i's to higher powers. The way I saw this being taught, and the way I read this originally when I first was a teacher, I was like, what? They want you to break this down into little factor trees and then count all the i's, and then every 4 i's that you count, you pull out as a value of 1, and it's a little bit of a mission. So instead of doing factor trees, guys, why don't we use our brain? Doesn't every 4 i's come out as 1? So guys, how many times does 4 go into these 38 i's?
9 times.
9 even times. And brothers, how many i's are left over?
0.
No.
2.
So guys, what's I squared? Bless you. -1, you're done. We'll do it again. How many times does 4 i's go into the 98 that were given? 24 times, actually. And this is 2 left over, so I squared is left over, so -1 is the answer here as well. Trust me, it's not always -1. For example, here 4 goes into 101, 25 even times with 1 I left over. So I to the first power is just I, or square root of -1, either or. I to the 43rd, 4 goes into 43 10 times with 3 left over. I cubed equals -I. Brothers, thank you so much. We're done. Yeah, let's go. Thank you so much, guys. God bless you. Have a great day.